Hello. So, the topic I will be handling for you people this semester would be one topic from physical chemistry, that is solutions. Uh, being students of chemistry, we are well, we are well versed, or we are very familiar with solutions, right? Because chemistry works in solutions itself. Whenever you want to do a reaction, you have to prepare solutions of the reactants along with catalysts, so many things. And even titrations, for example, you conduct in solutions. So basically, chemistry is a subject uh, which, uh, which I must say is a subject done inside solutions. But but the solutions what we are used to, mixing two liquids or mixing a solid with liquids, are not the only types of solutions. So if you look at the definition of solution, which is very, in fact, it's not a very rocket science. The definition of solution is, it's in fact our common experience what a solution is. A solution is a homogeneous mixture of two compounds. Any two compounds will not mix with each other, is it not? So only those compounds which mix with each other form an homogeneous mixture, and that mixture is called a solution. Take sodium chloride, you can dissolve in water. Glucose, urea, you can dissolve them in water. Alcohol liquid, you can dissolve that in water. Take benzene, toluene, they are soluble with each other. But there are also mixtures which are not soluble, in the sense they form heterogeneous mixtures. Oil plus water is a very popular example for heterogeneous mixtures. But how do we characterize solutions in terms of its components? In the sense, any solution has two parts. One is solute part, the other is the solvent part. How do we differentiate solute and solvent? We differentiate them by the amounts present. Solute generally is present to a lesser extent, lesser amount, whereas solvent is present relatively to an higher amount, higher concentration. Example, if I dissolve a spoon of sodium chloride in a liter of water, sodium chloride becomes the solute, solvent becomes the water becomes the solvent. Similarly, you take about 10 ml of alcohol, dissolve in 1 liter of water, alcohol becomes the solvent. But in fact, if you look at all types of solutions, we will come to know one thing, that solutions can be formed using solute and solvents in any state of matter. In fact, not just solid solute, liquid solvent, liquid solute, liquid solvent, the common solutions what we prepare in our chemistry. You can form solutions out of any state of matter, mixing in any state of matter. What is our atmosphere? What is our air? It is a mixture of various gases, nitrogen, oxygen, carbon dioxide. But isn't the air homogeneous? Is it heterogeneous? No, the air is homogeneous. Therefore, in fact, our whole atmosphere, the entire atmosphere is a gigantic solution of gases. Can we prepare a gas solute dissolve in liquid solvent, a solution? Yes, of course. You may have used these carbonated waters, cool drinks, soda. What are these? They are nothing but carbonated waters, means carbon dioxide is dissolved in water. Ordinarily, it doesn't dissolve in water. You can pressurize that and dissolve in water. So you get aerated waters as examples of gas liquid solutions. You have gas solid solutions also. Whenever a solvent is solid, or whenever solid is a solvent, it is a bit strange, surprising, is it not? Why? Because how can solid dissolve something else? If we have to understand this, we should imagine porous solids, basically porous solids which have a lot of space inside the lattice. Such porous solids can absorb gases. Hydrogen in palladium is one example. Hydrogen in palladium is a catalyst, is used in catalytic hydrogenation reactions. Hydrogen gas along with palladium catalyst can can do the convert the unsaturated bonds into saturated bonds, is it not? So that catalyst basically is an example of gas solute dissolved in solid solvent. Liquid solutions are very common. Liquid gas solutions are also common. I'm sorry, solid liquid solutions are very common, is it not? Sugar in water, salt in water, and many others, ionic salts dissolved in water. These are all examples. But how about a peculiar example here? Solid and solid. Solid solute with solid solvent. Is it possible? Yes, it is possible. How? Because if you look at alloys, what are alloys? Alloys are mixtures of two or more metals. And these alloys are homogeneous masses. Is it not? They are not heterogeneous. You cannot see separately metal A and metal B in an alloy. They are homogeneously dissolved to form an uniform concentration alloy. So brass, bronze, these are all alloys. How are alloys prepared usually? You take a solid metal, melt it, you add another metal to it, solidify it, you get an alloy. So alloy are best examples of solutions with solid solute, solid solvent. So stainless steel is an alloy basically, is it not? You have carbon dissolved in iron, which is the solute carbon. Why? Present in lower concentrations compared to iron. The solvent becomes iron. Therefore, solutions can be prepared mixing any states of matter into an homogeneous mixture. Now, in our chapter here, we are going to look into solutions of only one kind basically, which is that liquid solutions. Therefore, that makes our job bit easier. That makes our discussions bit easier, is it not? Because we are confined, we have limited our discussion to only one type of solutions, liquid plus liquid solutions. Now, since we are talking about liquids, one parameter of liquid we should know is the vapor pressure of liquid. Why this vapor pressure concept I am bringing in here? Because later we are going to classify solutions into ideal and non-ideal based on this parameter vapor pressures, values of vapor pressures. Now, let us know what this vapor pressure is. The vapor pressure concept you have already learnt in your lower semesters, maybe in your second semester, where basically when you are learning colligative property. Example, a non-volatile solute like sodium chloride, urea is dissolved in water. It leads to decrease in the vapor pressure of water. And this relative decrease in vapor pressure of a solvent by the addition of solute is a colligative property. So when you want to know which is a colligative vapor pressure, I mean, you want to understand colligative properties, you start with understanding vapor pressure concept. Vapor pressure is a pressure. It's like any other pressure. But how this pressure is created? You take a flask, put liquid in the flask and leave it. What happens? The liquid slowly gives out its vapors. And the vapors will escape into the atmosphere. And this process is called evaporation. If you leave this flask for some time, maybe for some liquid, some days, what happens? All the liquid would have got evaporated and the flask will remain empty, would be seen empty. But instead of having an open flask, you plug the flask with a cork. That means you are concealing the flask, you are containing the flask, you are enclosing the flask. So this is a closed container now. What happens to the vapors which are getting liberated from the liquid? They all collect on the surface of the liquid. Once they collect on the surface of the liquid, they start exerting pressure on the surface of the liquid. This pressure is called vapor pressure. So isn't vapor pressure a very simple thing to understand? Yes, of course, because the vapor pressure is the pressure of the vapors exerted on the surface of, or the pressure exerted by the vapors on the surface of the liquid when the system is enclosed in a closed container is called vapor pressure. Now, every liquid has its own vapor pressure at a given temperature. For example, at 25 degrees Celsius, I will take 4 liquids, 25 degrees Celsius, and I am preparing closed flasks of these 4 liquids: water, oil, maybe chloroform, petrol. What do you think? Do you think that all liquids will have equal pressure at that 25 degrees Celsius? No, definitely not, because liquids are having different degrees of volatility, is it not? Few liquids are very volatile like petrol, whereas few liquids are viscous like oil. Why is it viscous? Because the rate of evaporation is very less in viscous liquids. Why is it volatile? Because rate of evaporation or rate of vaporization, I should not call evaporation, rate of vaporization is rapid in case of volatile liquids. Therefore, at a given temperature, different liquids will have different vapor pressures. One factor. So what are the factors which control vapor pressure? One is the nature of the liquid itself, whether it is volatile, highly volatile, less volatile, viscous, highly viscous, such things. Now, I will take the same liquid, example water. At different temperatures, I will measure vapor pressures. Maybe at 25 degrees Celsius, 50 degrees Celsius, 90 degrees Celsius. Do you think all temperatures will give same values of vapor pressures? No. Why? Why? Because temperature increase will favor or will increase the rate of vaporization. Therefore, at higher temperatures, you will get lot of vapors. You will get more vapors. And naturally, if the amount of vapor increases inside the flask, the pressure exerted by the vapor also increases. Why? After all, how is the pressure felt? Because of the collisions of the particles, is it not? Now, if you are increasing more particles in the vapor phase, more particles of water in the vapor phase, they exert or they undergo more number of collisions, increasing the pressure. The collision can be with the surface of water, amongst themselves, or with the wall of the container, whatever it is. Increasing the concentration of vapor has a direct effect on vapor pressure. It increases the vapor pressure. So at higher temperature, vapor pressure is increased. Okay. This point I am just recalling from your previous semesters, because like for a pure liquid, you can measure vapor pressure. Vapor pressure can also be measured for solutions. Do you understand? Because we are going to discuss about solutions. Now, vapor pressure of pure liquid, you have understood. Extend this concept, extrapolate this concept to the vapor pressure of solutions. I have taken an example here. I have made solutions of two liquids, benzene and toluene. You look at the diagrams, benzene comprises of pure black particles, whereas toluene comprises of pure pink particles. But what about the mixture inside? Look at the vapors in the mixture. It comprises of both benzene vapors as well as toluene vapors. Now, if you measure the vapor pressure, isn't that vapor pressure contribution coming from both benzene and toluene? Yes, of course. The contribution comes from both benzene and toluene. Now, a simple question I will ask. If I have prepared an equimolar mixture of benzene and toluene, what do you mean by an equimolar mixture? Okay, this is the case study I am making. What is the case study? I have prepared an equimolar mixture of benzene and toluene. What do you mean by equimolar mixture? In a solution, to put it in a very gross way, 50% benzene is present and 50% toluene is present. This 50-50% I can express in percentage, or I can also express in mole fraction. So what do you mean by mole fraction? Mole fraction is equal to number of moles of component A divided by total number of moles of all the components. Now, because I have considered a binary solution. So what is a binary solution? A solution which contains only two components like benzene and toluene. I can write like this: number of moles of benzene divided by number of moles of benzene plus number of moles of toluene. So if that the value is 0.5, that means I have taken equimolar. Is it not? I have mixed benzene and toluene in equal proportions. Okay, fine. Now come back to the vapor pressure part. What is the vapor pressure of pure benzene? Not in solution, pure liquid benzene, 744 mm of Hg. What is the vapor pressure of pure toluene? 290 mm of Hg. Now I have made an equimolar mixture of benzene and toluene. What is the vapor pressure of the resulting solution? You should measure it actually. If you measure it, what is the temperature at which we are conducting this experiment? 79.6. Okay. You can measure vapor pressure at any temperature, not at room temperature always, because room temperature is always cozy and comfortable. We imagine conducting experiments in room temperature, but it is at an elevated temperature, 79.6 degrees Celsius. You can measure it. If you measure it, you get an answer of 517 mm of Hg. What is this 517 mm of Hg? Vapor pressure of the solution. Now, if you analyze how this value of 517 has come, you will realize that simply that 517 is an average of 744 and 290. So the vapor pressure of the solution, now equimolar mixture of benzene and toluene, is nothing but an average of vapor pressure of pure benzene and pure toluene. So this behavior is seen in benzene and toluene. Next question we are going to ask, is this behavior universal? In the sense, do all mixtures, equimolar mixture of all liquids, solutions, example water plus ethyl alcohol I will take, I will make an equimolar mixture. Are all mixtures going to give an vapor pressure which is an average of vapor pressures of pure A and pure B? No, in fact. Okay. There is a law called Raoults Law. You may have used this Raoults Law in your colligative properties chapter also. What does Raoults Law tell? Raoults Law tell the partial vapor pressure of a liquid in its solution is nothing but product of mole fraction and its vapor pressure in its pure liquid state. That means I can even express this Raoults Law in another way also. I can rewrite this. See here. What does Raoults Law tell? Raoults Law simply tells that vapor pressure of a compound or component in the solution, which is called the partial vapor pressure. What do you mean by partial vapor pressure? Partial vapor pressure is the vapor pressure of that vapors in the vapor phase coming out of a solution. Now, if I take pure benzene, if I measure vapor pressure, that is vapor pressure of benzene. If I take a mixture of benzene and toluene and I measure vapor pressure of benzene from the vapors collected out of the solution of benzene and toluene, that becomes partial vapor pressure. Partial because there is also vapors of other component. In pure benzene, the vapors are all vapors are of benzene molecules. In pure toluene, all vapors are of toluene molecules. But what about the solution? You get vapors, benzene molecules plus toluene molecules. What is the pressure contributed by only benzene molecules in this solution? That is the partial vapor pressure of benzene. What is the vapor pressure contributed by toluene molecules in the solution? Partial vapor pressure of toluene. Anyways, now let me express this Raoults Law in mathematical way. So vapor pressure of solution, partial vapor pressure of the solution is equal to mole fraction of the component into pure vapor pressure of that component. P is the vapor pressure of solution. X is the mole fraction of the solvent or solute. If you are taking two liquids, one liquid in lower concentration, that becomes solute. It is better if I tell mole fraction of component, not solvent solution, solvent solute, mole fraction of component. And what is P naught? Is the vapor pressure of the pure component. So how can I write the Raoults Law? Vapor pressure of solution is equal to mole fraction into vapor pressure of pure component. So go back to this slide. How to calculate mole fraction? I told you in my I told you previously, is it not? Number of moles of A divided by number of moles of A plus B. Why I am restricting my denominator to only two terms, Na and Nb? Because I am considering a binary mixture or a binary solution. If it is a ternary mixture, the mole fraction becomes number of moles of A divided by number of moles of A plus number of moles of B plus number of moles of C. Since it's a binary mixture, denominator is only Na plus Nb. Okay, you will get mole fraction. Now, since I have prepared an equimolar mixture in my previous discussion, the mole fraction is 0.5 of benzene and mole fraction of toluene is also 0.5. So multiply 0.5 by 744, which is the pure vapor pressure of benzene. You will get an answer. Multiply mole fraction of toluene 0.5 with 290 mm of Hg, which is the vapor pressure of toluene. You get one answer. You add both the answers, you get exactly 517 mm of Hg. So such mixtures which or such solutions which obey Raoult's law are called ideal solutions. So now we come to classification of solutions. Solutions are now classified into ideal and non-ideal solutions. What is the basic criteria of this classification? Ideal solutions obey Raoult's law. Non-ideal solutions do not obey Raoult's law. Now, characteristics of ideal solutions. The primary criteria, first criteria is obedience to Raoult's law. There are two more characteristics or two more criteria for of an ideal solution, characteristic of ideal solution. The enthalpy of mixing should be 0. Delta H mix should be 0. What do you mean by enthalpy of mixing? It is the heat change which occurs during mixing. If the solution, if the components are going to form ideal solutions, then during mixing, heat should not be liberated, should not be absorbed. There should be absolutely no heat change during mixing. Benzene plus toluene is an ideal solution. Why? If I mix benzene and toluene, heat is neither liberated nor absorbed. But you may have looked into some, while making some solutions in your laboratory, you would have experienced heat change does occur when making some solutions. Example, if you are making solutions of sulfuric acid in water, how do you make it? You take hydrochloric acid concentrated and mix it into water. Doesn't the solution become hot? Yes. Then that solution is not an ideal solution. Sometimes you dissolve some salts like ammonium chloride in water and touch the bottom of the test tube. The test tube is cold. Why? Because for the dissolution of ammonium chloride in water, heat has been absorbed. That solution is also not ideal. It is a non-ideal solution. Therefore, ideal solutions are those, apart from obeying Raoult's law, the enthalpy of mixing should be 0. As well as the volume change during mixing should also be 0. That means delta mix V should be 0. What do you mean by this volume change? I take 1 liter of benzene and 1 liter of toluene, mix them. What is the total volume now, or the volume of the solution expected? Because this is an ideal solution, the volume should be exactly equal to 2 liters. But this does not happen in all solutions. In non-ideal solutions, either the volume contracts or the volume expands. But in ideal solution, no contraction, no expansion. Delta V mix should be exactly equal to 0. Now, is there any idea about how to form ideal solutions? Which two components I have to mix? It has been noticed through experience that compounds which have almost identical structure or very similar structure when mixed form ideal solutions. Look into the structure of benzene and toluene. The structures are very near, very similar, except that toluene has an additional methyl group. Structures are same. So a combination of benzene and toluene gives ideal solutions. Now, coming back to some more examples of ideal solutions. Benzene and toluene we discussed at length. You can have combinations like hexane and heptane, N-hexane and N-heptane. What is the difference in structure, N-hexane and N-heptane? Hexane is 6 carbon atom. Heptane is 7 carbon atom. 1 CH2 extra in heptane. So the structures are very similar. Combination gives you ideal solution. Bromoethane, chloroethane. 1 bromine is substituted by 1 chlorine. Combination gives you ideal solutions. So there are in fact many more examples which I have depicted in my slide. These are all examples of ideal solutions. Now before I close the slideshow, this graph is what I want to explain. this graph has two origins on x-axis. One origin on the right and one origin on the left. The origin now is mole fractions. At one side, mole fraction is equal to 1. At other side, mole fraction is equal to 0. Mole fraction of A is equal to 1 in one origin. Mole fraction of A is 0. Mole fraction of B is 0 in that origin, whereas mole fraction of B is 1 in the other origin. That means mole fraction of A is equal to 1 represents pure A. Mole fraction of B, YB, mole fraction is actually represented using XB. Okay, fine. For our discussion, let us call it YB. YB is equal to 1 means what? At this origin, it is only pure B. What is in between two origins? You have different concentrations of A and B. Now look at how vapor pressure is varying. The vapor pressure of pure A is PA naught. The vapor pressure of pure B is PB naught. As you increase the concentration of B, the vapor pressure of the solution in between the extremes or in between the origins is the solutions. The solution's vapor pressure is linearly increasing as the concentration of B increases. So this linearity in the variation of the vapor pressure of the solution with respect to the concentration of the solutes in the solutions or concentration of any component in the solution, if the variation is linear, it means Raoults law is obeyed. Okay. In our next chapter or in our next discussion, not chapter, in our next discussion, we will see this linearity becomes distorted in non-ideal solutions. So next class, we are going to start with discussion on non-ideal solution and see how this linearity is distorted and why this linearity is distorted. Okay, fine. So I think we have discussed ideal solutions, and